All right. So starting from yesterday, so we started from a classical monochromatic electric field as a mode, a standing wave in a cavity, and the cavity mode basically. And then the cavity mode as a function of position, one-dimensional position jet, and T electric field we could express in this form. So E0 is the actual amplitude in the traveling wave mode or whatever, traveling forward propagating and backward propagating, and then uh, sine kz, sine omega t, that is actually your standing wave expression. And we introduced phi. If any phase is there, in general we can write like that, and then we express like that, and we find that there is one, we could decompose it into two terms. So one is a coefficient of sine omega t, and there is coefficient of cos omega t. Okay, so this coefficient, they are pi by 2 phase shift to each other at an instant of time. That's why we call them as a quadrature, field quadrature. And this field quadratures, again, we can just, since it is pi by 2 phase shift, so we can just express that in phasor diagram, that E0z e to the power I phi. So E0z is equal to E0 sin kz. So that is what we discussed yesterday. And then we to introduce a little bit of, so far we are in classical domain. So to introduce a bit about quantum concept, quantum photonic quantum mechanics viewpoint. So we could try to view this quadrature, two quadrature, in some kind of new type of expression, which is actually specially constructed to have it dimensionless. So it would be easier to handle dimensionless quantity. So one is sine omega t in terms of E naught, and this expression is multiplied, and this expression is multiplied. You know, V is the volume. So depending on the volume, basically your field quadratures actually depends. So volume, more volume, that means field quadrature will be expression will be more. So that is actually somewhat V is included actually in quadrature. Ultimately E naught that matters. So you have scaled with a V, and of course photon energy, all this type of thing. And again, sine omega t, cos omega t, they are two quadrature. Whatever we discussed in the previous slide, same way we are expressing. And assuming this this x1, x2, these are the two quadrature. And then if we try to express our electric field back again in terms of x1 and x2, we can write down like this. So where x1 and x2 is the field quadrature, we have expressed that omega t term, sine omega t term, and cos omega t term. Okay, so that way we could actually this thing, if we just use this 375 and go back to 369 and 370, where actually we have represented, we have introduced two variables, QT and PT, just to match with a electromagnetic mode to a harmonic oscillator. Okay, so PT and QT, and they were related something like this. PT equal to related to magnetic field, and QT is related to electric field, and they can be considered like this. Normal so-called your position and momentum of a simple harmonic oscillator. So in this form we have just kept, so that ultimately we get half p square omega square q square equal to this one. So that is what our intention. Now you see, if we have the expression for PT equal to this one and QT equal to this one, now you know this E0 sine omega t and E0 cos omega t we can express in terms of x1 and x2 field quadrature. So that means I can express this x1 x2 in terms of q and p. So that is what we did. X1 x2 we just represented in terms of qt and pt, because qt and pt they have a direct relationship with the classical or whatever simple harmonic oscillator we know, we have already represented here. So that is just for this type of treatment. Actually it helps to get some kind of visualization, some kind of correlation with quantum mechanics aspect. For example, to discuss this, to understand this, or to visualize this, we are just accepting some property of quantum mechanics like Heisenberg uncertainty principle. So far we have considered that this quadrature electric field you can actually express in terms of two quadratures, and two quadratures again they are proportional to some kind of position and momentum variables, time dependent of course. That is what we expressed. Again, you know, this position and momentum they are related with the uncertainty principle. That part only we want to bring, that quantum mechanics perspective we will bring here now to understand what this quadrature meant for. So now you see that is the quadrature, and we can express this quadrature x1 and x2 for entire electric field. This is your electric field, right? This is your electric field, and you have expressed in the coefficient of x1t and x2t. We can just simply think that x1 and x2 they are orthogonal, we can consider, because they are out of phase by omega pi by 2. So you can consider they are orthogonal. So this factor and this factor you can consider orthogonal. Orthogonal means perpendicular to each other, we mean to say. We can represent like that. So I can picturize this field in a plane of x1 and x2. So in a plane of x1 and x2, if you just represent that one, then you can express that because you know this x1 and x2, if you at any instant of time, if you just consider at any instant of x1 and x2, they are time independent. Just x1 square, x2 square, their amplitude if you consider in the phasor diagram. This is cos square omega t, this is sin square omega t. So that will be, if you just get, then it will be E naught b 4h cot omega half. So that will be the magnitude. So if you try to represent that electric field in x1 x2 plane, in quadrature plane, that means x1 is one in this direction, you are representing as a x1 unit, one quadrature, one component, and this direction another component you are representing. Then your field looks like that. This that will be the magnitude, and this will be the phase. Okay, this will be the phi, whatever you consider initial phi we can consider. So we can actually express our electric field in terms of this E naught is the magnitude and phi in a phasor form we can express. And then you know x1 again, you know that as a function of time it will be varying like a sin omega t, and x2 it will vary like a cos omega t. So if you just think about that, how it is sin omega t as a function of time, how x1t is varying, that is also you can express. Whatever x1 you are getting here, then you have to think about it is actually varying like a time dependent like this. Similarly true for x2. Right? Now we come back again, as I said that think of that because x1 and x2 they are related to kind of position and momentum, and we know simultaneously position and momentum cannot be measured. They follow some certain kind of uncertainty principle. So in that case we can expect that there will be some kind of uncertainties in x1 and some kind of uncertainties in x2 quadrature. So whatever x1 uncertainty is there, that delta x1, and whatever uncertainty in x2 is there, that is delta x2 we are expressing. Right? Now we know that x1 expression we know here. So if I see that some kind of uncertainty delta x1, that means it is this one multiplied by delta q. And uncertainty in x2 means basically this is constant. So whatever uncertainty comes in, P, that will be translated into x2. So if we try to write down delta x1 and delta x2, their multiplication, then you see delta x1, delta x2. So this one multiplied by this one. So what will be left over? 1 over 2h bar. Omega omega will be cancelled. So they are so all the parameter, all the scaling factors, etc. we are using so that we get a very nice formula at the end, as I said earlier. So we have used that way. That is how we got x1 and x2, and delta x1 delta x2 multiply, omega omega will cancel, then you will be getting 1 over 2h bar and delta q delta p. So that is what I have written here, 1 over 2h bar delta q delta p. Okay, so that is interesting now. Use equation 369 and by the use of equation 369 370, the above relation, because you know this delta q and delta p, again we can have relationship with the q and p related to x and p. So now you see delta q means square root of m delta x, and delta p means square root of 1 by square root of m delta px. So if you multiply them, square root of m will cancel. So delta x delta px. So basically delta q delta p is designed, constructed such that they are actually directly equal to delta x delta px. So that is what we mentioned here. Delta x1 and delta x2 means 1 over 2h bar, and this one is nothing but delta x delta px. Now we know this value quantum mechanically. This value is greater than h bar by 2. That is the uncertainty principle we have already somewhere we mentioned here. Delta x delta px greater than equal to h bar by 2. So if we put here h bar by 2, then you are getting 1 over 4. So that's the ultimate thing you wanted to have, because your x1 x2 are dimensionless. So delta x1 and delta x2 is also coming as a just simply a number, 1 over 4. So that is the uncertainty principle for so-called we can represent for a electromagnetic mode. And electromagnetic mode means if we can decompose the electromagnetic mode in two quadratures, pi by 2 phase shift or 90 degree to each other. Okay, so that is what delta x1 and delta x2, and that is 1 over 4 we are writing. So this is the uncertainty principle we normally follow for your electromagnetic wave. Okay, so electromagnetic wave, we can, of course, you can see that x1 and x2 again they are related to sin omega t and cos omega t, and they are related to again electric field and magnetic field, associated to electric field and magnetic field. So basically this delta x1 and delta x2, they are actually representing directly the electric field and magnetic field amplitude. Basically they are relating, but we are representing here as a quadrature and dimensionless. So now that is what we conclude. We therefore conclude that the field quadratures are subjected to quantum uncertainty in exact analogy to quantum uncertainty of the position and momentum of a harmonic oscillator. That's just conclusion we make. Now you see, right? You think about that, delta x1 and delta x2 equal to 1 over 4, and that means when we have just expressed this one here, this figure, if you see x1 and x2, and then we have uncertainty in x1 delta x1 and uncertainty in x2 delta x2. So that means suppose you have x2 prime to x2 plus dx2 delta x2 and x1 to x1 plus delta x1. This thing if you just do, then you can actually imagine two circles with uncertainty in x1 and uncertainty in x2. So you see there are two circles. So this is the x1 value and this is the uncertainty in x1, this additional extra part you are considering, and then this is also x2 and extra things are that is uncertainty. Now this is in principle your magnitude that means dimensionless magnitude of the electric field, this one. So that means this electric field, because of the uncertainty in x1 and x2, you can think of this this field will have some kind of uncertainty within this circle, because there will be delta x variation this side and delta x1 variation this side and delta x2 variation this side. So you can imagine that the tip of the field is not really now fixed constant. Tip of the field is some kind of fluctuations, some kind of uncertainty. If you try to measure some kind of uncertainty, you can expect. So that's the beauty of the uncertainty for electric field, right? So this E, this is actually corresponding to electric field. We have just represented here. This is actually proportional to electric field, dimensionless electric field. So that means electric field plus some kind of fluctuations is there. And if you just think about that, only one quadrature, only x1 part if you are just considering, then you see instead of that is actually earlier we have shown x1 as a sine function, sine omega t. If you just go back here, x1 equal to sine omega t, that is time dependent sine omega t. So as a function of sine omega t, you would get this type of sinusoidal curve. Now because of the uncertainty, that x1 will have some kind of uncertainty, that's why it is kind of little bit thicker line plotted here as a function of time. Okay, this is actually whatever the variation here, that is actually shown as the delta x1 uncertainty. That width of the curve, that is actually delta x1. And then what you see in a function of time, if you see, that means this is a one sinusoidal curve you can imagine, and another sinusoidal curve you can imagine little bit shifted. Okay, so that means your quadrature, each of the quadrature field, they will be fluctuating like this. Phase fluctuations will be like this. Okay, so about because it is a time dependent, as a function of time it will be shifting like this. So within delta phi it will be there. So that means we can imagine that any quadrature, if you imagine, there will be some kind of amplitude fluctuation as well as some kind of phase fluctuations will be there. Okay, and in this case we are putting circle assuming that delta x1 and delta x2, they are exactly equal to 1 over 2, so that their multiplication is giving 1 by 4, so that you get perfect circular. That's a wild approximation. You can always, they can vary also, or you can actually manipulate that. That is the beauty. So you can manipulate with your technology, the source you can design such that you can imagine that delta x1 is as small as possible, delta x1. So, but when delta x1 is smaller from this principle, because that is universally true from the uncertainty principle, delta x2 will be higher, but their multiplication 1 by 4. So in that case, if your delta x1 is reduced, and then delta x1 is delta x2 is increased, then you see this thing will be actually it will be reduced like this, and the shape of the circle will be changed now. Okay, so other way you can do also. Delta x2 can be smaller, and delta x1 can be relaxed. So that type of engineering is called squeezing of the electric field. So if you can squeeze, somehow you can squeeze that this phase variation, this delta phi is as small as possible. Okay, at the cost of that amplitude will be increased. Okay, so this type of thing, you can control the either it's an electric field as stable as possible or squeeze state. So when we say that the delta phi is varying, but the amplitude is somewhat fixed, then it is called actually coherent state. And in the other part, you will be getting different type of squeezing of the electromagnetic wave. Okay, now point is that with this simple approach, just considering Heisenberg uncertainty principle and analogy to a quantum mode, electromagnetic mode to a quantum harmonic oscillator, we could show that the field will be fluctuating like that, and assume that this length is actually classical length, and this delta x1, delta x2 coming from the quantum mechanical part. And classically, if you think that this field is zero, assume this field is zero classically. In spite of that, that quantum mechanical fluctuation part, delta x1 and delta x2, can exist. That means if you just reduce this amplitude to zero, then this field, this fluctuation field, collapses into origin, as shown in this figure. So it will be like this: delta x1 will be this side and delta x2 will be this side. So this thing will be there. Okay, that is what, for a it is analogous to your 0 point energy for a harmonic oscillator. Here also you can have a 0 point field. So this 0 point field, whatever is there, classically you cannot explain, but quantum mechanically this exists. And if that exists, if you are considering that the corresponding energy, that is vacuum. So absence of classical field is called vacuum. Here vacuum means it is not like absolute free space. It's a material can be there, but electric field is zero, for example. Classical electric field is zero. So that is called vacuum. So that vacuum, then corresponding energy for the electric field energy, half epsilon 0 E vacuum square. And you can imagine that magnetic field also carrying also similar type of energy. So you can actually consider 2 times of the whatever energy stored by the electric field. So if you just consider that is actually equivalent to what you call that 0 point energy, then you can calculate E vacuum. That this expression I have shown you earlier also, but here with this point of view, just considering quadrature point of view, also you can come out with a solution that E vacuum will be this much. So now here I think one quick thought you can think of, just thought problem, you can experiment type things. So when we consider this half h card omega, this is a 0 point energy, right? And this 0 point energy coming out of what you call that? It is coming out of a particular mode. But a cavity, like whenever I am considering a standing wave mode here, for example, where is that one? This is your one standing wave for a given k or given omega, right? K and omega, they are related. Omega by c equal to k. This is one particular mode. But you can think of different mode, different frequency, different mode can standing wave also can also exist for the same cavity. So in a cavity, you can think of huge number of modes will be there. Large number of modes will be there, right? So each of this mode, actually you are making analogous to your harmonic oscillator. And each harmonic oscillator, each mode, each harmonic oscillator. Then each time you supposed to get a 0 point energy. So in a cavity, you can imagine infinite number of modes, cavity modes, depending on your frequency, everything. So if it is so, then you can think of that if infinite number of oscillator is there or mode is there, so every mode will contribute some 0 point energy of half h card omega. So if you sum over all this 0 point energy, what you get? Infinity, right?
Be infinite. Yeah.
Is that acceptable?
I think, I mean, I've heard of this kind of a paradox, and like how they deal with it is through renormalization, right?
Yeah. So actually, this is not. This cannot be. This is a catastrophe. Another way. That's why I think. Another one theory. Actually, theory. You can say that calculation done. That it is not really. It is what you think about now, like black body radiation. Black body radiation, you know that it has a particular shape of radiation. So different oscillator strength will be different. That's why you don't get uniform emission everywhere. Okay, some kind of oscillator strength will be there. So that's that type of concept also introduced by Casimir, and try to calculate some some derive some expression, and that is actually called Casimir force. If it is a cavity, and that Casimir force actually that you cannot actually go beyond a certain value. So that is called Casimir force, because two plate is there. So this 0 point energy is being balanced or being stored as a Casimir force between the attractive force of two mirror, for example. If it is a cavity, some mirrors. So that type of things is there. So I'm not going into that detail, but you should keep in mind that that is not the case for all. But if you are considering a single mode, and then for single mode, whatever the vacuum field, you can consider that will work. If you have a few modes, then it is somewhat it works, that whatever the total 0 point energy vacuum works. But whenever you are considering that large number of modes present, and you are increasing, that time it will be just, if you just keep on adding one after another, so asymptotically it will be reducing, and it has some kind of upper limit will be there. So that thing I just wanted to mention. Okay, now,
Sir,
yes. Well,
sir, this 0 point energy is fairly a small number, right? Because half h cut omega
true.
is there.
Yes, true. It's a
But
fairly small value.
in terms of field quadratures, is a very big number. So
Uh,
that is field.
how
I
you
mean
say
field
that field
quadrature.
quadrature is big number?
The uncertainty is 1/4, which is and
That is a
here
number
in
just. That is a dimensionless number.
yes, sir. But 1/4 and here is h cut is there. So h cut is like
No, no,
10
no.
to the power
So
minus 34.
you see, this is this quadrature again. It is x1, and it depends on x1 and x2. X1, x2 expression is there. So if you see the x1, x2 expression itself, h cut omega is there also.
It's normalized in the uncertainty
Eh,
part, right?
Yes, 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 exactly. So ultimately, you are just putting delta x, and delta x1 and delta x2 will be there. If you are just using as a quadrature, that time, if it is dimensionless, you have to use some number. That is the number coming. And this energy, whatever energy, half h cut omega it is coming, that is coming from our harmonic oscillator 0 point energy, because this is not coming, whatever we are discussing so far classically. This is we have introduced again something like that Heisenberg uncertainty principle, whatever way we use here also we have used that. Okay, uh, quantum mechanical, if you solve a harmonic oscillator potential, you have half h cut omega will be there. So that half h cut omega will be when you consider classically, because Habich cut omega anyway you cannot explain classically, and this delta x1 delta x2, that is also not non-classical. So if that non-classical part, if you are considering when your classical part is reduced to 0, then this non-classical part, whatever the things is there, that you can actually consider that equivalent field is there. If you are just considering that field classical wave field, you see left hand side it is something we are calculating like classically, and right hand side is quantum mechanically. There is some kind of equivalent field we are considering. This type of field actually you cannot really access, but actually it was very recently with some experimental result, it has been measured as a Casimir force. This field is appear like a Casimir force. So that force could be measured actually, and you cannot utilize this force also, of course, for certain application. Okay,
So,
but it impacts a lot of measurement things. Yeah.
so sir, x del x1 del x2 is like classical effect, and
No,
the
delta x1 and x2 is quantum mechanical. It is quantum mechanical.
Right.
That is quantum mechanics. We have just considered uncertainty principle.
I mean,
Uns-
classical field when is there, then
huh,
we'll get
huh.
that.
So we are imposing that if there is some kind of uncertainty principle we impose on x1 and x2, because that is obvious if you are considering like a mode that is coming like that. And this part, this calculation, left hand side, we calculate like a simple like a electromagnetic theory, whatever the energy, pointing vector, all over equivalent field we are trying to calculate. Okay, so
That is
that is
only for vacuum, sir. Right?
that is vacuum. When you are considering classical field is zero. Still, this
Yes.
delta x1, delta, because it is in a phasor diagram, I just collapse this one, then it will be in the origin. So you have
Yes.
delta x1 and delta x2. That means that type of fluctuation field is there always, even in the vacuum. So that's a
Yes.
that is actually the you see, that is the heart of your quantum electrodynamics. This 0 point in us, and this fluctuation, that delta x1, delta x2. Quantum electrodynamics, everything actually, all the description, probabilistic measurement, everything that comes from that point of view. Though individually you cannot really, you can sense it, it is there, but you cannot utilize them for certain application. So this field, this energy, you cannot utilize. You cannot channelize for doing some work. That is what. If you can use this for doing some work, then it would be some from the vacuum. You are just from nothing. You are just trying to get some work done. That is impossible. But it is there. But it is there. It can influence your everything. Even in vacuum, that is actually field is zero, then that actually controls here. So this is one type of understanding that this field can fluctuate, and you know, this electric field, this is just a field, and we have this field, and it will have some kind of fluctuations will be there. Now we can actually think of explain this thing. This is just to get some kind of visualization, but ultimately electromagnetic theory, quantum electromagnetic theory, you can explain from operator point of view, quantum operator, you know, because now it is established that there will be some certain kind of quantum nature will exist. It's a semi-classical way we consider, but there is definitely possible that you can explain everything in quantum mechanical point of view. For example, you know, this electric field, you can imagine that this field strength is proportional to number of photon. Whenever I am considering this half h card omega, that means you have n plus half h card omega. You remember that that's n plus half h card omega, n plus half multiplied by h card omega. That n actually is nothing but a dagger a. You remember that a dagger a is equal to the number operator. Whenever we introduced a dagger, that's raising operator, lowering operator, when we introduced that, that thing actually is a dagger a together giving you photon, a number of photon. That means a dagger a can be considered as an operator, and if you operate on a coherent state, then you get a number. You remember that a dagger a and n, get n, then you would get n as a number. That means a dagger a gives the number of photon, right? A dagger a, if it is giving the number of photon means it is amplitude square. Amplitude square means classical amplitude, whatever classical amplitude square is basically proportional to photon number, right? Now we are considering only field. So instead of a dagger a, we can use just a or a dagger as an operator for this field. If you are just considering field as a quantum mechanical entity, then you can actually operate or field as a you can consider electric field, magnetic field, B, everything you can consider like a field operator. Then this you can get that operator proportional to just n basically. So that means, what I mean to say, that we can just now think of everything in operator point of view. This uncertainty and as well as your number of photon. And we have earlier learned about this coherent states, lasers. Lasers are basically coherent states, and this coherent states we could actually classically explain. Classical electric field is there, but whenever we are considering that coherent states, it's possible to manipulate, and you can squeeze the quadrature or this phase, etc. That means, can we not think a little bit of completely operator point of view, instead of just classical things, just completely we can treat electromagnetic wave as a quantum mechanical things and just get some results. So that is the new method. A lot of now textbook materials are available nowadays to treat the electromagnetic field as an operator and explain the coherent states and squeezed states also. So we'll be just discussing now in that point of view, and that part I will be covering from another book, Wolf Leonhard book, and that's a very nicely, very concise way it is there. I will try to explain maybe a couple of lectures from that book, and for that, just to understand about this coherent state and squeezed state, and what is their impact, and how to go for experimental results also, how to represent them and realize them, visualize them quantum mechanically. So one aspect we got semi-classically, something will be there. Now let us try to go for the quantum mechanical aspects. So I want to give you one quick recap. Whatever we understood about the state and operator earlier, this is just quickly, I have tried to document from that book only, because some of the parameters, variables, we have learned earlier, but they have used a little bit different symbol. But if we go through that, I think you will be comfortable with that. You will be recognizing what all those. So just quickly, I'll go through that, and from next class onwards, will be maybe 3-4 lectures I'll be taking from that book actually. You see, the state, the first point is the state of a perfectly prepared quantum object is described by Kate psi. That is what we know. And then, you know, the heart of the quantum mechanics is basically superposition of states, right? So any two or more states may be superposed to give a new state. That is what we learned earlier. And for example, if you have a psi 1 and psi 2 are two pure state, that means well-defined state, and then you can actually get some kind of combination, linear combination, you can get a new states. And C1, C2, these are the basically complex coefficient that we have discussed actually. Okay, so superposition is there. And then what we learned from this after superposition, you remember that we tried to express the state, quantum mechanical state, like a vector, state vector, right? Eigenvectors. So you could actually, you remember that we could define some kind of Hilbert space, and there can be a certain number of basis vector orthogonal to each other, and any state you can actually decompose into components of each of these basis vectors, right? So those things we have discussed. That is what I tried to document here. When we observe a physical quantity of an ensemble of equally prepared states, we obtain certain measurement value A with a probability PA. So this is just a little bit from the basics. Again, if you just read, you can relate that what you have learned earlier. That's the same thing it is being told. So suppose you have a certain state defined by Kate A, right? So this Kate A is a kind of state from where that's called eigenstate, and if you try to measure the particular state, say psi is there, and then you try to measure, for example, certain measurement values, you are getting A, and that A value you are getting with a probability PA. PA is defined. So some measurement, it can be momentum, it can be position, it can be anything, velocity, whatever. And that value you are getting A. And that value, measurement value, if you probability means if you are just equally preparing the state each time and then try to measure, then how many, what is the probability of getting that A value? That is actually called PA. And then once you measure to get a value, whatever probability is there, you somehow you got the value. For example, you measure the value, then the entire state will be collapsed into a state, so-called Kate A. We are defining, right? This is a Kate A. It is defined. Earlier it was psi somehow, but once we try to measure some value and we get a measured value with a probability A, then the entire state will be collapsed into such a fashion that if you measure again with 100% probability, you will be getting A, right? But when I say that probability, when you are getting PA, that means each time you are preparing this your entire system, like previous point, I measure now, okay, I get something, and then now again I assume that this system is prepared again previous way, then you measure, and then you measure again and again by preparing like that, and then you get the probability of finding A is PA. But once you measure with a probability A, then it will be a certain wave function Kate A. That is what the one of the axioms of quantum mechanics. We assume that it will be, once it is measured, then it will be collapsed into eigenstates. Okay, so if we prefer to assign a states only to ensemble of objects, a measurement produces statistical ensemble of states A with a probability PA. That is what I mentioned actually. So according to the superposition principle, we express the Kate psi, this one. So this you try to understand. We define a state, and that state you can define like this. You are taking, what is this one? The first one. First one is you are taking a projection with the A. That means dot product with A of that state vector, right? This is a bracket A psi, and that is a scalar value. This is a scalar value. Then this scalar value you are just multiplying with that eigenstate. So that will be actually your for a particular A value. Then you can consider another A, another basis vector, another value you will be getting, another basis vector, another value you will be getting. So in this way you will be getting a particular vector component basically. This is a sum of all this, you are just considering like this. Quantum mechanically you have considered, right? Now question, what is the probability for the transition from psi to a particular A? Mathematically how to express? I have a psi, and psi is expressed like this. That is it is a expansion basically. Basically this superposition here, whatever expressed here, that is actually mentioned here. So then the probability of getting a particular A eigenvector, that means one of the basis vector, we express like this. I think we have learned earlier that A psi, whatever you are getting, and you are just taking the mode square, and then you are getting a normalized, the entire value you normalize. That is means total probability and probability of certain collapsing into A. That's the ratio is the probability, right? And sometimes you can normalize this one, and that is what we consider psi here 9 number it is given here, and probability if it is normalized, then PA will be like this. And this one, this square, because this is a coefficient, right? Coefficient square and it's a scalar. This can be a complex value. This is a scalar but can be a complex value. That's why we are taking mode to get a probability. Okay, so then we can express like this. So that means probability can be expressed in this way. Okay, and all other things we just express, that normalization and orthogonality condition. For example, orthogonality condition is like you will have A, if there are two basis vectors, there will be just orthogonality condition. So that just to give you one recap. And also eigenvectors we have just expressed like this, right? The system of eigenvector must be complete. So this is actually It's a kind of, this is kind of operator called projection operator. Projection operator, for example, if you take dot product with psi, then you get a dot product here, and then you are multiplying here, then you get the component. That's why it is called projection operator. And that's can be, it should be complete, so its summation will be just 1. And then probability of all the things should be 1. That is what, from here actually you get this one. Probability of getting psi star, here get psi, brass psi, then it will be 1. Just mention that thing. And any average value, measurement values, A is given by. So this expression is also known, that A and probability A, probability of finding A, and then you sum over all the basis vectors. Then this can be written something like this, A times A, where A is like an operator. Now this A operator you can construct. That construction is nothing but PA expression you have already given earlier, right? Whatever the PA expression it is here, this is a PA expression, right? This PA expression, if you are just putting here PA expression you are putting, then you can construct this type of thing as an operator, where A, this first A is the actually eigenvalue. That means whatever the measure value and probability of finding that measure value and sum overall. So that is actually, you can get a certain value you measure. That means you need to know the value, probability of finding a certain value for collapsing into a particular state vector, and then you have to take sum over all things. That is actually how you get a operator in a matrix form for measuring something. And normally, since all the measurement A values, everything you supposed to get real, that's why this is Hermitian. All this we have discussed, right? Okay, so I stop here. Maybe after that, I'll just take, because all these things, whatever we are discussing, that will be using not only for explaining that that whatever the quadrature, squeezed states, etc., coherent states, as well as coherent states we have discussed earlier. We just touch upon again whatever we have discussed just to relate here. And most important thing is that another important quantum mechanical phenomena will be explaining, that called entangled state. What does it mean, entangled state? And because that entangled state and squeezed state and bounced, anti-bounced, all these things actually is useful for different type of again quantum photonics application, information processing. For example, entangled state is used for teleportation and heralding single photons, all those type of things. So I just want to quick recap whatever we have discussed earlier. I will giving that recap, and whatever I missed, I have not discussed earlier, particularly when we will call states are pure states, mixed state, and entangled state. And from there, I will be just moving on to the discussion of squeezed state. So you just go back again, whatever you have discussed before quiz 1, whatever the quantum state and vector state and how to handle them mathematically, orthogonalization, all those type of things. So we'll be again using for next few classes.